Okay, so welcome back. Now we're going to talk about prime numbers and prime factors. Okay, so what's a prime number? A prime number is defined as any number that only has two divisors, one and itself. Now, before we go any further, I want to make sure that everybody understands that the number one is not a prime number. It's considered a unit. Okay, why is one not a prime number? Because it doesn't have two divisors. It only has one. Okay, so we don't call one a prime. One is not a prime. It's a unit. We call it the unit. Okay, so what's the first prime then? 2. In fact, 2 is the only even prime. Okay, all the other primes are odd. Okay, because any other even number is automatically a multiple of 2. Okay, so now, so what are some of the prime numbers? Well, we have 2, 3, 5, 7, 11, 13, 17, 23, 29, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So those are prime numbers. I mean, you could keep going. 31, right? 31 is a prime number. 37, 41, 43, 47. In fact, there are an infinite number of prime numbers. Okay, in fact, just so you know, maybe something interesting to look up is this is where cryptography, the idea of codes, encrypting, you know, you send an email and it says it's encrypted emails, or you go to a website and it's encrypted for security purposes so people can't hack in. Well, a lot of that stuff is based on this idea of what we call not necessarily prime numbers, but I forgot what it's called. It's called approximately prime. Okay, which is, again, I'm beyond the scope of this course. But the idea of a prime number is that there are an infinite number of primes, and when you get large numbers, it becomes increasingly difficult to test whether it's a prime number again. Okay, so why are we doing this? Well, because there's this idea of prime factors. Because it turns out that every number has a unique prime factorization. So as you've seen in the other video, there's many different primes that you can, or not primes, but many different factors of a number. But if you look at just the prime factors of a number, then there's only one unique prime factorization for each and every number. Okay? So we can describe any number, any distinct number, by its own prime factorization. So let me give you an example. So if we look at 15, let's look at 15. So again, 15 has the factors 1, 3, 5, and 15. Okay, but what are the prime factors of 15? So this is a list of factors, but what are the prime factors of 15? Which means if I was to represent 15 as a product of primes, how would I do it? Well, it would be equal to what? It'd be 3 times 5. Right? So this is the only way I can represent 15. In fact, no other number can be represented with this set of primes. Okay? None. So this would be the prime factorization of 15. Now, how do we get, now again, for these types of things, it's pretty easy. But what if we get other numbers that are bigger that maybe it's not obvious what the prime factorizations are? And that's where we use as a factor tree. So let's do an example. of a factor tree. So let's say I have the example of 132. And I want to find all of the prime factors of 132 that I can multiply together to equal 132. Well, the first thing I do is the prime factor tree. Here's the algorithm. This is how it works. You start with the smallest prime, 2, right? So you ask yourself, is 132 divided by 2? The answer is yes. So what you do is you put 2 out here and you say, okay, 2 divided into 132 gives me what? So it gives me 67, right? Or, I'm sorry, not 67. 66. Okay, so now it worked. Okay, now, but I continue with 2 until I can't divide by 2 anymore. So 66 even. So I can divide by 2 again. So I'm going to put 2 here. So 2 goes into 66. That leaves me 33. Now I'm done with 2. There's no more prime factors of 2. So now I go to the next prime, which is 3. So 3 goes into 33 11 times. Now, guess what? 3 does not go to 11. In fact, 11 is prime. So now, guess what? I'm done. So the prime factorization of 132 is this. It equals 2 times 2 times 3 times 11. And that's the prime factorization of 132. Have a great day.